the gaseous state. And what's the big deal? Man, it could be a chemical reaction. You could be making Snicker bars. I'm not sure what the case is, but a lot of times you're involving gases. And you could be generating a gas. You could be using a gas. But regardless, what's going to be the pressure of that gas? How much gas are you going to generate? I mean, what's the temperature of your system? All those things really affect what I think is probably the most important point. Is probably the pressure, right? Because if you don't make your predictions right, and don't take things into account, some bad things could happen. So with the gaseous state, that's what I'd like to start with, is pressure. But what are some units for pressure that you've heard of? Oscar, what are some units for pressure what's a unit of pressure that you've heard of before? ATM for atmospheres. How about another one? Jorge, another one. Set of units for pressure. And your tire rim, those tires, they all have these units. Fill it up to this P S I. What does it stand for? Anybody know? Pounds per square inch. Pounds per square inch, which is exactly what pressure is. It's force per unit area, right? The force exerted over a certain area, that's pressure. How about some more? Let's see. There might be one more, Diana. One more set of units. Atmospheres, PSI. Does anyone remember? Anyone familiar with any more of them? There's Pascal, P-A, Pascal. That's another one. Use that a lot in advanced chemistry classes. There's millimeters of
mercury.
Hg, mercury, right? So there's a bunch. Okay. The one that I'm really kind of interested in, the one that I like, is this pounds per square inch, because, well, we're Americans, so I'm more familiar with it, but atmospheric pressure. If you take 1 square inch, which is probably like that, put it at sea level on a tabletop, and just that column, that 1 square inch of column of air goes all the way up to space, several miles. So that's a lot of air, right? Several miles of air. At the very bottom, that 1 square inch has the weight of all the air above it. And that weight is right about 14.7 pounds. About a little baby, right? Oh, kind of fat baby. It's substantial, right? 15 pounds every square inch. So if you take an aluminum can and take all the square inches on there, right? And then, it's 14.7 pounds for every square inch. It adds up to be about 150 pounds. And aluminum can is pretty dang easy to smash. Why doesn't it get smashed? I'm telling you, there's 150 pounds of pressure on this thing from all directions. Because what's inside? Air, too. 14.7 pounds per square inches on the inside, too. You've never, ever felt atmospheric pressure. Pretty much because it's also inside you. The only time I think I have felt pressure, this physical pressure, is when I was brave enough to swim to the bottom of the 10-foot pool. Then I felt pressure, right? I felt the water pressure. But if I would have swallowed a bunch of water, the pressure would have equilibrated. I wouldn't have felt it. I'd be dead, but I wouldn't have felt it, right? That's the idea. So if I can remove all the pressure, all the air inside this can, I would have just created a what? Starts the V, a vacuum. Well, that's what I want to do. I'm going to put a little bit of water in there. I'm going to remove all the air inside that can. How I'm going to do it is, you saw me put a little bit of water in there. That little bit of water inside the can, I'm going to boil it. And once it gets boiling and you see a bunch of steam shooting out of the can, you'll just have to take it on faith. There is no more air in there. It's all steam. But when it's boiling and steam is shooting out the top, the pressure is still 14.7 pounds per square inch. Otherwise, the can would be crushed. Something's going to happen to it. So I'll just replace the air with 14.7 pounds per square inch of steam. So if you're inside there, I mean, you couldn't breathe. There's no oxygen. It'd be really hot, too. But okay. So when I get the can full of steam, flip it upside down inside the cold water, what happens to the steam? The C word. It condenses, right? Steam, when it's around something cold, it's going to turn into a liquid. So it'll condense. So all that steam at 14.7 pounds per square inch inside that can, it just turns into a very thin film of water inside the can. Well, then I just generated a vacuum. So the can should what? Once I put it in the cold water, it should crush, right? From all sides? Should it be violent? Or it'll just be kind of slow? 150 pounds of pressure. It's like, I don't know, just stepping on the thing, right? I do this kind of quick. All right. So it's about the only way to prove to you that there's atmospheric pressure. Because you can't feel it. Right? You can't feel it. It's all sides. Instantly. You've been at a restaurant, just like I've been, and you've been sitting there waiting, and you play with the straws, right? You fill up the straw, you put your finger on the end. Does stuff leak out? No, right? It doesn't leak out. Why not? Because shouldn't it be dripping out? Because this water's pretty dang heavy. Something's got to be pushing back up. Yeah, I'm blocking the atmospheric pressure. Because now I just have this little tiny bit of air above here. So there's that much pressure due to the air. There's not very much mass there, though, so there's not a whole lot of mass there. But there's a lot of mass here, but it's still not dripping out. What's pushing up at the end? At 14.7 pounds per square inch. What's pushing up? Atmospheric pressure at 14.7 pounds per square inch. That's a lot. So if I want this stuff to actually start dripping out, well, I just need to make this column of liquid, what? Make it longer, taller, right? Make that liquid, make this glass column of liquid a lot taller. So tall that it'll finally start dripping out. Right? Because the weight would finally overcome what atmospheric pressure is. Make sense? How tall would that column have to be? Not tall enough. I need 5 of these. 10.2 meters, and liquid water will actually start dripping out. So, I mean, it would be environmentally safe. I mean, weathermen could use this. 10.2 meter high column of water, and the barometric pressure is 10.1 meters of water, right? And they could do that, but they don't. What do they fill the glass tube with? Not water. They fill it with mercury. Where is it? Fill it with mercury. What movie had mercury in it? Terminator. Terminator, which one? Don't you remember? The street and all that silver metals out there, they shot him with a shotgun and did everything to that dang Terminator. It was the second one, right? And then the silver metal all comes back together and rebuilds the guy. That was mercury, right? The only metal at room temp that's a liquid. Okay. So they use mercury. So then if you use mercury, it's only 7.6 meters high, 760 centimeters. 76 centimeters or 760 millimeters of mercury. So you'll see stuff like this. You'll see, I give you all these conversions. Whoop. 1 atmosphere is 760 millimeters of mercury. Because you take 760 millimeters of mercury high, and it'll start dripping out. That's 1 atmosphere. Okay. Here's where the guts of the chapter is, though, predicting final pressure, temperature, or volume of a gas. So you're going to be messing with it somehow. And pretty much you have to mess with the pressure, the temperature, the volume, and everything else will change on you. But for example, Jonathan, what happens to gas pressure if I lower the temperature? Pressure goes down. Can you visualize why? I think it goes to this, and what I need is a movie of this thing, right? Here's a little piston. The little piston can go up or down, right? And all it depends on is these little blue balls, and they're the gas molecules slamming onto that piston. So they're slamming onto it so often with such a force. Well, if I make it, let's make it hotter. If I make it hotter, these little gas molecules start moving what? Faster or slower? Faster. Make it hotter, they start moving faster. They slam into that movable piston even harder and more often. Well, that's higher pressure. Jonathan's right. Make it colder. These little gas molecules start moving slower. They don't hit near as often, and they don't hit near as hard. Less pressure. Okay? Any planet that has nitrogen, mostly nitrogen, in the atmosphere has a blue sky. We have a blue sky. Mars doesn't, right? If I take air and I make it really cold, 330 degrees Fahrenheit below zero, so negative 330 degrees Fahrenheit, I can make air turn into a liquid. Well, that's what this is, right? And they call it liquid nitrogen. But my hand is close to 100 degrees Fahrenheit, negative 330 degrees Fahrenheit. There's over 400 degree difference. So you'd think it would really hurt. But it just kind of pricks because it boils off so fast. I'm burning up in comparison to this thing. I pour this 330 degrees Fahrenheit onto this balloon. What's going to happen to the balloon? Good guess. But pop is a good guess. But I think the only way for me to say that it's not going to pop is you got to play around with liquid nitrogen a lot. And you find out it doesn't do anything to rubber. It doesn't do jack. So kind of like a penny. It won't do anything. What would happen to this balloon? Pop, isn't it? It's shrink. Because what? The balloon shrinks because the air pressure inside, the temperature gets colder, so gas molecules aren't moving around so fast. They don't hit the sides. Because that's why the balloon has its shape in the first place. Because, well, you got the rubber there, but the air inside's hitting it, right? Giving it that shape. Right? Yeah. But once I stop pouring the liquid nitrogen on it, see what happens. It starts getting what? Get it up here. It starts getting bigger again, right? Why does it start getting bigger again? Yeah, pressure's building up. Why? It's reheating and getting back to room temp, right? All right. So, okay. Where are we here? So we need some mathematical equation if we're going to make predictions. The ideal gas law. PV equals nRT. Okay. Out of all those variables, one actually isn't a variable. It's used the same for all gases, and it's just a number. Which variable is it? Does anybody know? They call it the gas constant. No, it's not N. They call it the gas constant. It's actually big R. And for all gases, its number is 0.0821. Okay. Now, but the number, I don't think, is the insightful part. The insightful part are the units for that. And I give you all these constants, right? Liters, atmospheres, over moles, Kelvin. Okay? So just by looking at those units, you can pretty much figure out how to use the ideal gas law, I think. Danielle, P is probably what of the gas? Pressure of the gas. And Erica, not only is P the pressure of the gas, if we're going to use that equation, it pretty much needs to be in what units according to this R? P is the pressure of the gas, and it pretty much needs to be in what units? It has to be. Does anyone see it? ATM has to be in atmospheres. And there's, like we said, there's several units of pressure, so you got to convert it into atmospheres, whatever, if you're going to use that equation. How about volume? Oscar. Volume is not the volume of the gas, and it better be in liters if you're going to use that equation. How about T? Christian. Kelvin. Now, how do you get to Kelvin? Right? Every single homework question gives you degrees Celsius. You have to add something to it, and you'll get Kelvin. What's that number, Alejandro? You said it. 273. Add 273 to whatever the Celsius is they give you in the question, and that's how you convert to Kelvin. Notice there's no degree sign on Kelvin. You just say Kelvin. Okay, that's T. We know what R is. That leaves little n. Little n. Oh, Clarissa. Little n has to be what? We used all the units but one. In R, we used all the units but one. It's the moles. Little n has to be the moles. The amount of the gas. That's what little n is, the amount of the gas. And it has to be in moles. Odds are, though, Katrina, I bet the homework question is not going to give you moles of the gas. They're going to give you the amount of the gas in what units? Fine, grams. How do we go, Katrina, from grams to moles of the gas, which is what we have to use this equation? Not mole bridge, molar mass. Molar mass. Okay. Let's rearrange the ideal gas law. PV, divide both sides by nRT. It'll look like this. All right, if you divide both sides by nRT, add some subscripts, because we want to predict final. That means there has to be initials. So let's write our initials. P1, V1, N1, R, T1. Now, it doesn't make sense, though, to put a subscript on the R, because there's no initial R, final R. Right? I mean, that can never change, so I'm not going to put a subscript on that one. Well, if the initials all equal 1, the finals all equal 1, too. I'm going to use 2's for my finals. Well, they both equal 1, so that means they both equal the same thing. They equal each other. Right? And I can cancel, here's my equation, but I can simplify it. Every single time, what cancels? No matter what my pressures and volumes are. The R's. And then the book is going to say, they're never going to change the amount of gas on you. They're always going to keep it in this container. They're never going to add gas. They're never going to remove gas. So I can pretty much cancel what also? Anybody? The n's. That's kind of ugly, so let's just rewrite it. It would be like P1 V1 over T1 equals P2 V2 over T2. That is the equation we're going to be using for the homework. But there's kind of a trick to it. We have to realize, we'll say that the temperature must always be in units of Kelvin, right? They don't care about pressure. They don't care about volume. They just have to be consistent on both sides. So the units of pressure and the units of volume just have to be the same on both sides. They don't care. Temperature, though, has to be Kelvin. So Annabelle, in this equation, how many variables do we have? 3 there. 6 total. So Tegan, how many variables do they have to give you in every single problem? 5. These are going to be wordy problems, right? But most everybody, I think, is kind of like me in the sense that they're lazy. So they're not going to give you all 5. They're going to say, the temperature is constant. Well, then you can cancel what, Erica? The temperature is constant. And there's all these other words in there. We can cancel what then? The temperatures are constant. Cancel the T's, right? Because the temperatures. And they didn't say what the temperature is. They just say it's constant. The volume is constant. Cancel the V's. The pressure is constant. Cancel the P's. That's how it's going to work. I'm sure they're going to do that in a lot of the questions. Okay? And that's about it. Okay. So to make this as complicated as possible, this is a quiz question, and I give you all this stuff. Right? I give you these 2 equations. I have to give you what R is. And then I need to give you all these conversions, like there's 760 millimeters of mercury. In an atmosphere. Maybe even more conversions if there's more units of pressure, right? Okay, let's see if we can work this out. A sample of nitrogen gas at 18 degrees Celsius and 760 millimeters of mercury has a volume of 3.92 milliliters. What is the volume at 0 degrees Celsius and 1 atmosphere? Okay. Alejandro, seems to me it's a gas, obviously, and we only have 2 gas equations to work with. Which one fits? The first one. Why does the first one fit? You're right. Yeah, it's giving you an initial. In other words, they give you 2 temperatures. They give you 2 volumes, 2 pressures. Whenever you see that, there's an initial and a final. Does everyone see what he's thinking? Right, they give you an initial. Okay. So we're going to have to use this one. So that means, this is how I like to do them. I just like to list everything out. Because those P1, B1, and T1 all have to correspond. And I can get them all in the right units over here. Do the same thing with the P2, the V2, and the T2. Get everything in nice, consistent units. Then I'll plug everything into my equation and plug and chug and get my answer. So we have to know 5 of those 6 variables. Oh, we haven't picked on yet. Diana, can you name one of these variables for me? T2 would be 0 degrees Celsius. Okay. Plus the 273. Great. So that's really going to be 273 Kelvin. Okay, we've got the T2. Another one. Annabelle. Yeah, I think so. I agree. And let's get it into Kelvin right away. So what's 273 plus 18? Well, 291? 291? Right? Ah! Thanks. I thought it said T1. I'm blind. So 18, thank you. I should have just changed the P1. 18 degrees Celsius plus 273 is 291. Okay, another one. Daisy. V1 would be 3.92 milliliters. Okay. Should we change it to liters? We can. If we change it to liters, and then V2 will be needs to be in liters too. Does the question care? You're looking for the volume, but remember, this is the one that has to be in liters. Because of that R, that's why. But in this one, if he's in milliliters, this one will just come out to be in milliliters. So we can just leave it alone. Our answer will just be in milliliters then. They didn't even care. So I would say just leave it alone. How about another one? Tegan, how about another one? Another variable. 760 millimeters of mercury is P1. Okay, which we have two more. We have to know one of them. Christian? P2 is 1 ATM. All right, now you got to make a choice. Do you want to work in? You see how it's nice to list them out? Because it's obvious. Your units aren't consistent. So do you want to work in millimeters of mercury or atmospheres? Okay, let's work in atmospheres. You want to work in atmospheres? So we got to change him to atmospheres.
Well, wouldn't it be better just to work in volume?
They're equal. Aren't we going to cancel them out anyway?
The units will cancel out, but that's why they got to be in. They have to be consistent. So it doesn't matter which one, either millimeters of mercury or atmospheres. The only time it matters, remember, is this equation because you're using R. That's the only time you have no choice, and P has to be in ATM. Because look at that R. It's right here. But we're not using that equation, so boom, don't worry about it. And Christian said atmosphere, so let's just convert 760 millimeters of mercury in an atmosphere. Kind of silly. Comes out to be 1 atmosphere, right? The 760s canceled on us. Okay. V2 is what we're looking for. Plug everything in and see how this works. P1 is 1. V1 is 3.92. T1 is 291. That has to equal P2, which is 1. V2, which is all we're solving for, and T2, which is 273. See how this is a great problem for those, right? It's moving things along a diagonal. V2 is already up on top, so leave it alone. The only thing you got to do is move that 273 over. So whatever's on top, multiply, bottom divide. You get an answer. What did you get? 3.68, around 3.7. Here around 3.7. So Erica agrees. And the units have to be what? Milliliters. Okay? So you do this one. See if you can set this one up. And remember, the game plan is just to figure out what the equation is. Then just list out all the variables. Then plug and chug. Substitute, then plug and chug. you're not sure where to start, just ask. So Dulce, what equation are you going to be using?
Is it the P1V1?
Yeah, it's the P1V1, right? Because you see, there's multiple temperatures in there. There's multiple of everything. So it has to be the P1V1 equation. Right. I agree with that. List everything out. They got to be in there somewhere. To me, these problems aren't so bad. It's just the English. It's how they word these things that gets confusing. What's the confusing part or the trick to doing this one? Have you seen it? It's the same what? Pressure. You have to assume the pressure doesn't change on you. When you read that question, it says the pressure's 1 atm, so you scribble down 1 atm. And you start filling out everything else, but you realize, I don't have a P2. Oh, yeah, you do. You have to assume the pressure didn't change. I agree. I think that's the trick to doing this one. Okay. Annabelle, what did you plug in for your V1?
Is it the 2.54?
Yeah, liters. Okay. And T1? Diana? Which is how many Kelvin? 295. Okay. The other side, how about V2, Jonathan? Yeah. Oh, yeah. Okay, good. That's what we're looking for, right? Okay. T2. 76 Kelvin. So it was negative 197 degrees Celsius. You said it's 76, so I guess you add 273 to that, you get 2. Okay, everybody agrees. You get 76. Plug it all in. You solve for V2. What'd you get? 0.65 liters. Anybody else get that? Yeah. Okay. Are you comfortable with it? Okay. So far, it doesn't look that bad. I mean, it's a nice Monday because, right, all we're doing is pretty much this equation, what the homework appears like it's doing. List everything out, plug and chug, okay? I think the only real trick question to this is this type of question right here. And let me give you a hint. The trick to figuring it out is pretty much writing a balanced chemical equation. So read it over, see if you can write a balanced chemical equation for this. And that really is the trick to doing this. If you're not sure, just ask. See what to do? To form methanol. H is an H2.
Okay.
Hydrogen gas, hopefully you're writing it on the reactant side, it's actually H2. I don't know if you knew that, but it's H2. All those gases pretty much are, except for the nobles. Nobles are the only ones who aren't diatomic. Hydrogen, oxygen, nitrogen, fluorine, they're all diatomic. Okay, so let's see if you got it. So Oscar, what did you write as your reactants? Hydrogen gas and carbon dioxide gas. What did you write as your products? Oh, Tegan, what did you write as your products? The CH3OH and H2O gas. What did you put, Jonathan, as a subscript on your CH3OH? What? You need a little subscript on there. Solid, liquid, or gas? Liquid. Okay. Have to have it balanced. Jorge, how'd you balance it? Okay, carbons. Carbons are done, right? It's 1C, 1C. Oxygens, 2 and 2. We're good there. Hydrogens, okay. So how many hydrogens on the product side? Count 6. Yeah, because 3 and 1 is 4 and 2 is 6. So what do we need to put in front of the H2 then? Put you need 6 of them. 4 would make it. That'd make it 8. That'd be too many. So make it 3. Yeah, good deal. So we'll have 6 hydrogens. Now we're done. Nice and balanced. So the weird question is after they gave you all the description, they said how many volumes of hydrogen are required for each volume of carbon dioxide. Usually they say moles, right? I mean, with our mole bridge idea, we'd say 3 moles of H2 react for every 1 mole of CO2. So we said moles, but they're talking about volumes. So the trick to doing this is just realizing, well, PV equals nRT, but PV over RT is really just N. And if we said P over RT times V. I just kind of rearranged it a little bit because they said that same temperature and pressure. So you're talking about these gases and they have the same temperature and pressure. Well, dang. They have the same P and T, but R is also the same. So the number of moles equals volume for this ideal gas law. So you can talk in, doesn't matter whether you're talking in terms of moles or if you're talking in terms of volume, it's the same thing. It's kind of odd. So you could say, I don't know, instead of saying 3 moles of H2 for every 1 mole of CO2, you could say 3 volumes of H2 for every 1 volume of CO2. And the volume could be milliliters. Fine. 3 milliliters of hydrogen gas for every 1 milliliter of carbon dioxide gas. So the question is, how many volumes of hydrogen are required for each volume of carbon dioxide? You would say 3. Ah, 3. Okay. Not so bad. So, man, you even get that out early today. Isn't that nice? No lab this week. Okay. So try the homework, come by. I'll be glad to work on some of these questions with you.